David Smith here with one more flipped classroom math video lesson. 3 tips before we start. First, remember you can adjust the playback speed to make it faster or slower as you like. Second, you can pause the video at any point to catch up on your notes or jot down some questions. Third, you can turn on the captions so you can read my words on the screen. Today's topic, the derivative rule. So as you know, we've been working through this process of calculating derivatives by using a lot of individual computations. To do that, algebra provides a really simple way to calculate the derivative. But remember, the way you've been doing it so far in class gives you a fundamental understanding of what derivatives are that you don't get from just a plug and chug method like this. So to underline what you need to know for my course is you're going to need to know how to do this the way we've been doing it, which is calculating average speed for a very short time interval approaching the point for which we want to know the instantaneous speed, which is the slope of the tangent line, which is the derivative. Okay? So this process is going to show you how to calculate or how to find the derivative function that you can then plug in and find an instantaneous rate really quick. So in this course, you can use this process to verify answers quickly and easily, and you'll know if you got it right. But remember, you need to do it the way we've been doing it in class to get full points on a quiz or a test. Okay, let's get started. So, derivative rule. It's pretty straightforward. If f of x, if our function is some coefficient times x to some power, then the derivative, denoted by f prime of x, is going to be take that number that the power is, multiply it by the coefficient a, and then reduce the power by 1. Now this looks a little bit more complicated than it works out in practice, so let's do one. If f of x is 6x squared, then what we do is we take the power, that's the 2, and multiply it by the coefficient, so power coefficient, power times the coefficient, so that becomes 12, bring our x across, now we reduce the power by 1, so that goes to x to the first power, which is just x. So this is the derivative function for this function. Okay? In a minute, I'm going to show you how to use the derivative function to get instantaneous rates. But right now, we just have the derivative function. Now let's do one that's a little bit more complex. Same rule, but now we have 3 terms in our function. So f of x in this case is 3x squared plus 2x minus 9. So that's a very typical quadratic equation. Now, let's take the derivative of that and find the derivative function. So, first term, take my power, multiply it by my coefficient, so that becomes 6, bring my x down, and I reduce the 2 by 1, so that's just plain old 6x. Bring down my plus. Now this one, you can still use this rule to evaluate this term. We have x to the 1, so that's going to be 1 times 2, that brings my 2 down, and now I have x to the 0, because I'm subtracting that 1. So anything to the 0 power is 1. So I'm done. 6x plus 2. 9 doesn't have a variable on it. There's no x, so we just drop that off. The constant goes away. Okay? So that's the derivative function for this function. Okay, let's move on to one of our problems from the Green Book to talk about how to use a derivative function to find an instantaneous rate at any point in time. Okay? So here's our function for page 251, to the rescue. This is the supply bundle that got dropped from the helicopter. The helicopter is 400 feet above the ground, and the object starts falling due to gravity, due to this part of our equation. This is a quadratic, by the way, so we're just going to use the quadratic part of the derivative rule to figure this out. Okay? So let's find the derivative function. I'm going to rearrange this just a little bit. H of t is minus 16t squared plus 400. This is typically how we write quadratics, so I've changed it around a little bit. You don't have to do that, but I think it makes a little more sense. So let's find our derivative function. That would be h prime of t. Now I take my 2, multiply it by the negative 16, and reduce that by 1 to 1. So this is going to be 2 times negative 16 is minus 32t. The constant goes away. Boom. So here's my derivative function. Now you're probably thinking, how do I use that? How do I find an instantaneous speed? It's super simple. You just plug in a value for t, whatever time you want, and this function will give you the instantaneous speed at that time. So for example, let's say we want to know how fast is the supply bundle falling at 3.5 seconds. Okay? So we would do h prime of 3.5 equals minus 32 times 3.5. It's that simple. Okay? So again, to review, what you do is you first take your function, you find your derivative function, and then you plug in the time for which you want the instantaneous rate into the function, and that gives you your solution. Needed my calculator for this one. So, 3.5 times minus 32 equals. So this gives us minus 112, and our units on this I think are feet per second. Okay? So at 3.5 seconds, it's falling at negative 112 feet per second. It's falling down. The negative is just because it's going down. The speed is increasing in the negative direction. Okay, I want to show you this graphically, and I'll remind you of a few points about instantaneous rates, derivatives, and slopes of tangent lines. Okay, so I have my graph here. This is time in seconds, and this is height, which we go height as a function of time. And notice it's not h prime, it's just h of t, because that graph is for this function, and we know that we're at 400 feet up here, and that's 0 feet there. Okay? So as the object is falling, it's falling at a faster and faster rate, so it covers more distance for the same amount of time. Okay? Now I've marked off our seconds. We remember that it hits the ground at 5 seconds. 3.5 seconds is right there, so I made my dashed line up to the curve. So that's where the object is. Its height would be whatever that height is, and the time is 3.5. So as we've talked about in class, the slope of this tangent line is the instantaneous rate. We just found that here. So this is 112 feet per second. That's the slope of that tangent line. The derivative of this is minus 112. So remember, all these three things are the same. Instantaneous rate, slope of tangent line, derivative. Okay? So to summarize, put it all together. Here's our function. To be able to calculate the instantaneous rate at a point in time, we first get the derivative function. We use the derivative rule, and we change that function into the derivative function, which we denote h prime of t. Then we can use the derivative function to find instantaneous rates at any time along the function. All we do is we just plug in the time that we're interested in into the derivative function, and it spits out the derivative, which is the instantaneous rate at that point in time, which is the slope of this tangent line at that point. Now that you've watched the video, take a moment to jot down any additional notes, some questions, or a quick summary of the lesson. You can also re-watch the portions of the video that were a little bit challenging for you. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.